Hello. Now we will calculate some other variables for isothermal process like work done and the internal energy and the heat given to the process. Okay. So let's start with work done. Now in case of work done, you know the formula for work done is PdV for closed process where the piston is there. So when the process is closed and if you know for us system is always closed system. So work done is defined as PdV. And if you remember the isothermal process, the equation for isothermal process is T is equals to constant, and I'm writing that as T naught, which is the constant, or we can say PV is equals to constant and that value is equals to R T naught. We are dealing with 1 mole of gas. Okay, or let's put the n number of gas. So if we have to calculate this work done, so this P is also a variable if you can see, and the volume is also a variable. I cannot outrightly integrate this function. And to integrate this function, I have to convert the variable. Here you see the 3 variable, I have to change the 3 variable system into the 2 variable system. For that, I'll use this equation. In this equation, if you see, I can write P as nR T naught upon V. And this value, I can replace in this equation. Okay, so work done dW will become, in place of P, I'll write nR T naught upon V dV. Or we can say it will become dW nR T naught, this is a constant, dV upon V. And this function, if you see, right hand side there is a variable V, on the left hand side there is a variable W. If I integrate this function from V1 to V2, now 1 is at state 1 and P2 is at state 2. So initially, obviously, when you are starting the things, the work done will be 0, so Wg. On doing the calculation on integrating this function, we will get Wg. And I have put the limits here itself because Wg minus 0 it will be. And if I integrate this function dV upon V, it will give me log function which is ln V, where we have to put the limits V1 and V2. On putting the limits, dWg will be equals to nR T naught ln V2 upon V1. Okay, so this is the work done. So in case of isothermal process, temperature will remain constant, volume and the pressure will keep changing. Depending upon the change in volume, we can calculate how much work is being done onto the gas. Oh sorry, how much work is done by the gas there. This is the work done by gas. Here we are different from chemistry. In case of chemistry, they calculate the work done onto the gas and we calculate the work done by the gas. That's why in chemistry, if you see, the negative sign always comes there. So you see, this is in terms of volume. And we have one more relationship, this one. So the same relationship, we can apply it here also. So you see, the pressure is given like that. So we can say P1, V1 is nR T naught as well as P2, V2 is equals to nR T naught. So what I did, I satisfied the state 1 and the state 2 from ideal gas equation. I put the values, and state 1 and state 2 temperature is constant. Only thing which is changing is the pressure and volume there. So if I divide this function, it will be P1 V1 divided by P2 V2 is equals to 1. Or we can say it will become V2 upon V1, I'm taking this value onto the right hand side, will be equals to P1 upon P2. So V2 upon V1 becomes P1 upon P2 in case of isothermal process, and this is the isothermal process. So what I can do, this equation which gives us the work done by gas, I can replace this value there. So that will give me Wg is equals to nR T naught ln P1 upon P2. So now I'm having, it's a single formula for calculating the work done by gas, but one in terms of volume change and other in terms of pressure change. Okay, so this is our work done by the gas formula in case of isothermal process. Now let's go for calculating the internal energy. So if you remember, the internal energy for any process is having the same formula. The formula for internal energy, change in internal energy for the gas, that is equals to nCV dt, where if you want to write the value of CV, that is F by 2R. So this will become this F by 2 by R. Let's put that value also. So du will be equals to NFR by 2 dt. That is your change in internal energy, whether it is an isothermal process or adiabatic or any process. The change in internal energy is the same, which depends upon temperature. Okay, but if you see here the temperature dt, this is an isothermal process, and in case of isothermal process, dt is not changing. The temperature is not changing at all. So since dt is 0, so based upon that I can say the du will be 0. So in case of isothermal process, change in internal energy does not happen. Whatever amount of heat you give to the process, whatever amount of heat, whatever work you do, the temperature is going to remain constant. So if the temperature is going to remain constant, the internal energy of the whole system is not going to change there. Okay, so this is your du for isothermal process. Let's go calculating the heat. So from first law, if you see, from first law of thermodynamics, if you see, the formula is dq is du plus dwg. This is the formula. So in this formula, dq is the heat given to the process, du is the change in internal energy of the process, and the dwg is the work done by the gas. So for isothermal process, we have calculated this as well as this. Let's put the value. So for isothermal process, dq, meaning I am calculating for isothermal process, I put the T, dq is equals to 0 plus nr T naught ln V2 upon V1. Or we can say dq is equals to nr T naught ln V2 upon V1, or we can have the equation in terms of pressure change also. So this is the heat given to the process, given to the isothermal process. Okay. So if you remember, we always used to calculate the heat capacity, and the heat capacity for isothermal process, heat capacity for isothermal process Ct will be equals to dq upon dt at T constant. But the thing is, temperature is not going to change here. So dt value will always be 0. So heat capacity for isothermal process will be infinity. So whatever amount of heat you transfer to the system which is performing the isothermal process, the temperature of the system is not going to change. Okay. So if you remember, one more time we'll proceed there. So work done, when we started calculating the work done, the formula is dw is equals to pdv. That's the general formula for any closed system, not for open system, only for closed system where the piston work is done by the piston. So this is the equation. This is the equation representing these two are the equation representing the isothermal process. So what we did, we replaced the value of P into the equation, and then we integrated that. After integration, we get the work done as this much. So work done we calculated in terms of change in volume, dV2 upon V1. Okay. Then by replacing the volume by the pressure, we got work done formula in terms of pressure also. And when we calculate the change in internal energy, the formula is same. It is irrespective of the process. So when we applied the formula, we came to know that in case of isothermal process, dt is always 0. So change in internal energy, whatever happened, is 0 in case of isothermal process. Then we went by first law of thermodynamics. From first law of thermodynamics, we put the value of change in internal energy as well as the work done by gas, and we calculated the work, the heat given to the system, and which was equals to work done by the gas. So whatever heat you provide to the system, the whole amount of heat, the system will be utilizing whole amount of heat to do the work. So in this case, there is no loss kind of thing is happening. Whatever heat you are giving to a system, the system is utilizing whole heat and doing work according to that. Okay. So that's your, and the heat capacity when we calculate for isothermal process, that came out to be infinity, since the temperature was not changing whatever amount of heat you give to the system. Okay. Thank you.